If you've always just relied on solutions, you're going to fall on your face in some of these problems. They can be confusing.
It doesn't matter.
355 and 71 are all pointless. Those are really easy.
All right, which one do you want to do?
Let's do 51. Well, unless you want to do 50, I think
Nah,
they're the same.
I'm fine.
Which one? Which one?
51.
You want
I
51?
think they're the same thing.
All right,
Well,
what is it? Give me it. I got
Two spherical conductive shells.
All right, now this is such a good problem, by the way. A and B, and it's surrounded by something
And they're
that's got
surrounded by-
conductivity, right?
yeah, just a sigma.
All right, what is the sigma? Constant?
It's just sigma.
It
It's
just
just sigma.
says,
Oh, okay. All
I
right,
want
this
you
is a
just to-
no-brainer. I'm going to do a perturbation on it. So this is a constant, just sigma naught, right? They want the resistance, right? So they want the resistance between here and here, the effective resistance, okay? With me on this? So the way you would do a problem like this, and I'm just going to tell you this. You're going to assume I, because I'm going to change this problem, and I want to see how you think about it. You're going to assume I, then you're going to get J. And J, of course, is I over the area, which will vary versus radius that it penetrates through. With me on this? And it is a vector. That will be a vector. Then from there, you're going to get E, which is J over sigma. Follow me? Assume I, get J, then get E, and then to get V, you integrate E dot dl, in our case from A to B. And this, you always worry about the magnitude of voltage. Finally, your last step is to get R, and R is just V over I. With me? This is the way it always works, and I'll show you how the parallel for the capacitor in a second, okay? Now, we assume I, we get J. What is J going to be? Now, do you all agree it's a spherically symmetric problem? First, we have to maintain that. Do you agree, class? If it's spherically symmetric, the current is going to flow with the same intensity in every direction. Now, this is kind of not exact, but what I'm saying is if I come out a distance R away, and I make a spherical shell through that, all the current penetrating through that shell will be the same regardless of where R is. Do you agree with that? Now what we're really saying, if you want a better picture of this, I'm saying I'm putting the current I in here. Assume you drill a little hole, that insulated, and it comes to the inner conductor. This is supposedly insulated, all right? And then you ground this outer conductor. So all the current goes in, hits this shell, and it flows radially outward. Y'all follow this? You can think of it this way. The current's flowing in this direction. All right. Well, that value of J will be I divided by the surface area of that sphere. What's the surface area of a sphere?
4 pi r squared.
That's right. And it would be in the AR direction. Now, if you know it, fine. But I want to make sure, bless you, that you say it, bless you. Okay? Now, what is E going to be? Just the J over sigma, correct? I think this is a classic problem in physics too, but I don't remember exactly. So that's going to be I over 4 pi, and then it's going to be sigma naught R squared AR. And that would be amps per meter squared. Do you agree with that, class? Amps divided by meter squared, amps per meter squared, correct? Sorry, that's J. This is E is volts per meter.
Yeah.
This is amps per meter squared. This is volts per meter. All right, now I need to get the voltage. V, and I'll call it VAB. That's going to be the integral of E dot dl from the inner to the outer, just magnitude. You don't have to worry about sign. So that's going to be the integral of 1 over 4 pi sigma naught divided by R squared AR, A to B, magnitude of that dot dl. And what is the differential length if we're in spherical coordinates, we're going outwards this way? Now, you remember? I'll tell you, what is the differential length in spherical coordinates in general? And this you can think about. It's always going to be dr AR plus, or really it's going to be that plus, and it's going to be r d theta a theta plus r sine theta, and then it's going to be d phi A phi. That's the unit vector. Y'all with me? I mean, it's a differential length, pardon me. Differential length. If you dot that, only the AR component survives. Do y'all follow me? When you dot AR dot A phi, it's 0. AR dot A theta, it's 0. AR dot A phi, it's 0. With me?
Mm-hmm.
You got a question there?
Yeah, I was just wondering if I guess we just need to know that. There's no like, we don't get any of that on the quiz or test.
A what?
What that is, DL.
Well, it's only going to end up being that.
Yeah, I know that for this, but like, you won't give us like the entire DL for spherical. But we'd have to just know it ourselves for quizzes.
Well, should know it, but you remember that thing I sent everybody? I gave you differential volumes, surfaces, and lengths in all the coordinate systems.
Yeah.
Did you see that thing? You know what I'm talking about, right?
Yeah.
All right, that has it all there.
Okay.
Now for a test, if you want this, I'll give it to you.
I do, yeah.
All right, I can give it to you, but really, if you actually think about this, think about the differential, can't even draw this thing today. Right? Remember how we did this?
Yeah, I do.
All right, the differential length. Outwards, it's dr, right? This way, it's simply r d theta, and this way, oh boy, I can't even draw it. This way, it's going to be r sine theta d phi. Well, if you just take this dr ar, r d phi, and it's r d theta, a theta, r sine theta d phi, a phi. That's how I remember. Okay. Anyway, back to this thing. So it's just gonna, I'm just gonna put down dr because the dot product's gonna get rid of the other two components. When I do that, what do I get? I get 1 over 4 pi sigma, right? Sigma naught. And then I integrate ar dot ar is going to be 1. What's the integral of 1 over r squared?
Where'd our I go?
It became a 1.
Can we bring the I out of the integral too?
Sure.
Okay.
We can bring the I.
Wait, isn't it the negative integral? But I guess it cancels anyways.
Yeah.
Well, the way I'm trying to tell you to think about it, it's the magnitude. Technically, it's what? It's the integral from a to b with a minus sign, right?
Okay.
All right, but I'm going to tell you, if you get something that's a minus value there, just make it a magnitude, because your resistance is voltage over current. It's always positive, unless it's really a
I guess you
nonlinear.
could just change your
You
could change your
just put a
points of
minus there and
contact.
you're going to get it. But what's the integral of 1 over r squared? It's minus 1 over r, right? And then when you switch the limits, so you get this, and it's going to be what? 1 over a minus 1 over b. Do you all agree with that? 1 over a is greater than 1 over b because a is less than b. Finally, what is the resistance going to be? Well, it's V over I.
So it'd just be 1 over.
So it's 1 over this stuff. The I's cancel it. I will always cancel. So it's 4 pi sigma naught over 1 over A minus 1 over B. Okay. Go ahead. What's your question?
Why is it A minus B and not B minus A? Am I just like
Well,
missing
here's
something? Oh,
the
it's the,
tech-
I see it. It's the
Here's the technical
Yeah, I got you,
integration. This, right? Now, when you integrate that, right, you get minus 1 over that and switch the actual thing, and 1 over A goes first. Okay.
Yeah, I got you.
But I try to tell you to do the math. You can't mess that up. So that's the resistance. You all agree with that? Something to note. As B goes to infinity, it simply becomes 4 pi sigma naught A. Now, in many, many problems, and by the way, this is for a whole sphere. I'm going to try to show you some tricks that I think are beneficial. Ready? Sure. First one is going to be, well, what if this conductivity was not a constant? So the next problem, I'm going to leave this there, all this, and what I'm going to do is show you something. So the next part of this is, instead of the conductivity being constant, and I do this all the time in quizzes. Look at my old tests and quizzes and final exams, you're going to see this. So if I say that sigma is now equal to sigma naught divided by r, instead of just sigma naught, now what happens to the resistance? All right, let's start out. We assume I, right? Next, we're going to get J. J is not a function of the conductivity per se. It's what? That over 4 pi r squared A r, sorry. It's going to be I over 4 pi r squared, and this would be amps per meter, right? Square meter squared. You agree with that? This would be J, let's say. This would be J. I better just do this right. You agree with that, class? Right, I over the surface area, correct? All right, what's E going to be? J divided by, say it. J is sigma E, right? So if we take, to get E, we take J over sigma, right? All right. So it's going to be this.
JR over sigma naught.
Keep watching, yes. Over 4 pi r squared divided by sigma, which is sigma naught over r. AR. You can see what happens. One of the r's cancels. You all see that?
Yes.
So I get r squared divided by r, or just r. Just bear with me. So this is going to be 1 over 4 pi sigma naught r. Now I got to get the voltage. What's the voltage going to be? Do a magnitude. It's the integral from A to B. Technically, I'll tell you what, I'll just show you. If you go like this, put a minus sign there. And it's equal to the integral of I over 4 pi r AR dot BR AR. I'm not going to do the whole differential there. And I integrate that, right? And that becomes what? I over 4 pi, right? Integral of 1 over r is natural log, correct?
Yep.
And it's going to be, I can do the magnitude thing, times the natural log of B over A, right? Agreed, class? Finally, what happens? Then my resistance is V over I equal to what?
You dropped your
I
sigma.
forgot my sigma.
Yeah.
Yeah, sorry. Sigma. So it's going to be 4 pi sigma naught natural log of B over A. Correct?
Mm-hmm.
Does everybody follow me in this? You may want to sit up. Well, sit up. I'm not trying to go too far afield, but y'all follow me. Okay? Keep watching. I'm going through all the permutations. Now this is a classic problem that really happens in the real world. And I'm going to erase this. Is it really almost 140?
Oh, Dr. McGinty.
Yeah.
Can you post any old tests on campus?
Just go to Ada Capinu, they got everything. Or just look, I mean, Ada Capinu has everything. You know what Ada Capinu is? They have all my stuff, all right? You can, I know what my tests are. By the way, don't just study tests. You really want to look at the homework. That's where I draw from.
Mm-hmm.
If some people say, well, the tests you had before don't look like your homework. I mean, don't look. The prior tests don't look like the tests we just took. And I said, yeah, but they look like the homework. That's where I draw from. I don't draw necessarily from old tests because we've changed textbooks and stuff like this, everything. I changed a lot of stuff. All right. But they have all my old tests if you're interested. It doesn't hurt. Sometimes I think people think, well, this is what he's going to put on the test. It has to be one of these, right? You got 20 problems. It's usually not any of them. But nobody's had me before here, have you? Nope. Chase isn't here. He's had me, he can tell you. The fellow in the back, and we're missing one other guy. We're missing
three.
There's a couple
Wait, are people? Do you know if people have dropped the class?
They dropped the day is what happened because it's Friday and they want the Mondays we don't go.
Yeah, well, a whole week off. So.
I didn't get one drop notice yet.
Okay. So
But-
we should have 10 people. I
Yeah,
think. So
well,
we're missing half the people.
I'm missing him. I know two of them, Chase and that fella. Don't even know his name. He's a foreign national. But who else?
Jackson.
Oh yeah.
That guy that I don't know his name, and then someone. Oh yeah, that guy. Oh, is there one over there too?
Okay. So I'm missing. But you know what I know? Monday's off, right? People pick up because of this. If there's a quiz, there'd be more. But if there's a quiz, there'd be. Hey, listen, I'm sorry about that severe weather stuff, but really, I thought it was better and I got permission. I really don't like coming up here when I think World War III is going to happen with the weather, because I've been on campus when bad tornadoes happen a couple times. And tornadoes, the one thing you really don't want to get caught in if you're in a car or outside, because they can pummel you. By the way, anybody have hail in here? Where you're? We talked about this earlier.
Yeah, it was in
Some
Burbank.
people had hail south, 10 minutes south of us. They had hail in Montgomery. They had quarter-size hail, I was told by Michael Smith, the fellow that records the lectures. And but I mean, there's been hail all around. We didn't get it, thank God. But hail you don't want, because your car. We've had really bad hail a couple times. Not here in Auburn when I was here, but in Montgomery they did. And I mean, it looked like a ball-peen hammer, nuts on all the cars. You really, so if you think hail's going to take your car and stick it under a concrete deck or something. Okay, now here's one that's classic, and I asked this kind of question. Instead of a full sphere, suppose you only had half a sphere. So what I'm showing you is, trying to show you is, I got something like this. This is going to be half a sphere of radius A. We'll cut right through the chase. So here's what it looks like from the side view. Inner radius A, outer radius B here, but I'm going to call it all constant. And I'm going to say it has sigma naught. And I want to know what the resistance is. If this was a meter, I want to know what resistance it would measure from the outer surface, we might as well ground that, to the inner surface. How would you do that? This is an ohm meter. This always helps, because most people use ohm meters, so this is an ohm meter. So what resistance would you measure? How would you do that part? This is a classic.
You set your current as an arbitrary current.
Start with the current assumption, right?
Yeah.
We're going to assume a certain amount of current going in here. I'm going to assume it's I. Now, your senses are right. So that means J is going to be I divided by the area, right?
2 pi r squared?
That's right. Now
It's
it's
just
only
half
half the area. Exactly.
It's just
You're good at that. So now it's half the surface area of the sphere. Follow me? And it will be symmetrically distributed, guaranteed. So now it's going to be over, instead of 4 pi, it's 2 pi r squared AR. Y'all follow me? I want to tell you, this has application. What I'm showing you, I'm going to tell you right now, it's got an application. And it has to do with really being an electrician in something called a grounding rod. But we'll talk more about this. It's going to be a grounding half sphere for this one. So now, how do I get E, guys?
J over sigma.
J over sigma. I made it constant, which is nice. So that's going to be equal to I over 2 pi sigma naught r squared AR. I want to take a gander with the voltages, because that's the next thing, right? Start with I, get J, get E, get V. What's the voltage going to be, magnitude-wise?
The integral from A to B of E.
Of E of this, which is I over 2 pi sigma naught r squared AR dot, and then it's dr AR, right? So that's going to be equal to I over 2 pi sigma naught. Technically it's minus 1 over r. Switch the limits here, or minus times minus, it becomes 1 over A minus 1 over B. And just put a magnitude there so you don't mess it up. That's the voltage. What's the resistance? It's V over I, right? That's V. That means it's simply going to be one over 2 pi sigma naught, and then it's going to be times 1 over A minus 1 over B. Y'all agree with that?
Yeah.
I want to make a comment on this. Now this is something I just want you to take a look at for a second. Normally when they do problems like this and they talk about grounding rods, if I take a look at this and I assume this dimension B tends to infinity. With me? What happens? If B goes to infinity, R becomes approximately simply 1 over 2 pi sigma naught A. Y'all follow me on that?
Yes.
Now, in the real world, and I'm not an expert on this, but if you wanted to get an approximation of the ground conductivity, assuming it's uniform, this is an assumption, but in some cases, a lot of cases, it's true. What they'll do is, out a long ways away, they'll drive a grounding rod, say 20 meters away. They'll put a rod deep. You know what an electrical grounding rod is? It's about 8 to 10 feet long. It's solid steel typically, maybe copper plated, and they get it into the ground, and it's firmly like driven into it. And then what they'll do, in this case, it's usually not that. It's usually they pound another rod in. But if this is a half sphere of a known distance, and they measure the actual radius, then they can say they can get this conductivity by simply taking its 1 over 2 pi resistance measured divided by A would be the conductivity, and they could get the soil conductivity. Do you all see that? That's an assumption, though, that the conductivity is going to be homogeneous. Usually what they do for calculating things like that is they'll take a rod and they'll drive it down, deep rod. And then they'll put a grounding rod out there. So now it looks like a cylinder with an infinite actual ground. Follow me on this, class? Now, I'm not going to do that problem right now, but I'm just giving you an application of this. You can use this to estimate the actual conductivity of the soil. I think I mentioned this here. Do you remember what the conductivity of air is? I told you this. Do you remember me telling you this?
Is this the 10 to the minus 5 number?
It's 10 to the minus 14,
Oh,
to
okay.
10 to the minus 15th, roughly. Sometimes it's about 10 to the minus 5 times 10 to the minus 14, all right? And it's 1 over ohmmeters. That's here, right? Very, very high conductivity. So think about this just with me for a second. Suppose, you ever do the balloon thing? Rub a balloon, put it on a wall? Well, the time constant, I better not do the whole thing. If you want to get the time constant decay of that charge, which is like the RC time constant for a circuit, you can approximate that balloon's radius. Follow me? And then approximate the discharge point at infinity and get the resistance between that spherical thing and infinity. That's the R. Then we can get the capacitance. And then the time constant, do you remember the time constant for RC circuits? Tau, it's e to the minus t over tau. Tau was RC. Do you remember that? We can do something exactly like that for anything where we can approximate the capacitance resistance and figure out how long that charge, how long it takes that charge to dissipate, like one time constant. I'll show you this stuff, but it's interesting. And by the way, it's very accurate. But what is very interesting about a lot of this stuff, even though it looks like, boy, gross estimations, it's actually very accurate. You know, with balloons, what's the thing that holds them up? Well, it's the electrostatic attraction to the wall, right? Usually the wall, or whatever it is, or the ceiling if you put it on the ceiling. What's the thing opposing or pulling it down? Gravity. So if you can estimate the mass of that balloon, and you can estimate the attractive force on the wall, now you have to get this thing called the frictional, it's the coefficient of static friction. You can actually figure about how much, what electrostatic force it will take to drive it in the wall before it starts falling. And it's amazing how this stuff actually works out so well. So I'll get to that later. But now, so that's a couple of things with resistance. One last thing with resistance I want to ask you. Tell me your gut feel on this. So here, I'm going to take a sphere in a radius A, and I'm going to divide it in half. Just tell me your gut feel on this. And half of it is going to have a conductivity sigma 1, and the other half is sigma 2. And this, say I ground the outer part. What's the effective resistance between the inner and outer conductor? How would you do it? I bet you know. Half of it's got sigma 1, half of it's got sigma 2.
Would you treat it like two resistors in parallel?
That's right. We just did half the resistance, right? We did one where we had sigma naught, right? And it was, I mean, just sigma naught, but we have only half a sphere, right? We figured that resistance out. So what you would do is this. You would say, it looks like this. It looks like I've got a resistance here where it would be R of a half sphere with sigma 1 in parallel with R of a full sphere, a half sphere with sigma 2. Y'all with me? Follow me? Does that make sense to everybody? Out of curiosity, what would that be? Well, this we figured was what? That was 1 over 2 pi sigma 1 times 1 over A times 1 over B. Do you agree with that? This would be 1 over 2 pi sigma 2 times 1 over A, 1 over B, minus 1 over B, right?
Yeah.
They're in parallel, it would be 1 over the first plus 1 over the second. So, if you take a look at this, for this one, I'll just put it here. The R equivalent for this one is going to be 1 over the first one. And the first one was 1 over 2 pi sigma 1, and it's times 1 over A minus 1 over B, right? Plus 1 over 2 pi sigma 2, and it's times 1 over A minus 1 over B. Can you all follow me? Y'all agree with that? Now, you can go ahead and manipulate that, but you're going to see a couple things happen. I forgot to do that.
The second one over.
Yeah, I got to put 1 over that. 1 over 2 pi sigma 2, 1 over A minus 1 over B. I'm sorry about that. Now, if you take a look at that, and you can manipulate that, the 2 pi sigma comes on top. 2 pi sigma 2 comes on top here, right? Then I've got 1 over this over that. This stuff comes on top. Y'all follow me? Y'all with me on this? All right, so you can get it that way. Now, what about this? I'm showing you all the things of permutations. And by the way, out of curiosity, what happens if instead of half, suppose a quarter of it has sigma 1, and the other is sigma 2.
Then instead of using a half, we'd still put them in parallel, but instead of using a half, it'd be 1/4 and 3/4.
Okay, now you have to think about quadrant ones. Think about this. Your gut's instincts, right? If you think about this, there are 8 quadrants, right? There's 4 up top, 4 up bottom, right? Mm-hmm. I'm saying I'm in the lower quadrant here.
Wouldn't that be you mean the octant?
Octants.
Okay, then it'd be,
okay. So it's 1/8. Y'all follow me? Half, 1/8 the area would be here, if you think about it, right? The other 7/8 is there. So then you would proportionally do it that way. Y'all follow me?
Yeah.
And it gets really, you can think this through, but it's obvious when you think about it. Okay? How about the next one? These are all permutations of that same problem. And I'm doing it in spherical, it's holes for cylindrical. Tell me your gut feel about this. Inner radius A, then an outer radius here of B, and the first layer is going to have sigma 1, then followed by another layer with sigma 2 out to radius C. And I want to know the effective resistance between A and C. Ground that one. How would you do that? Think about it. Yeah.
So you get the resistances of the two and then put them in series.
Exactly. You
And
all
so
see that?
you integrate for the voltages for the first one from A to B and the second one from B to C.
But yeah, and you know what? You already know what the resistance is for constant sigma, right?
Mm-hmm.
So from here to here, you'd put that resistance from A to B. Then from B to C, you'd put that resistance in series and add. Y'all see that? And you could go through every permutation. Maybe, and I've done this on exams. I'll put the outer one, half of it's got sigma 1, half sigma 2, and then the inner one's got sigma 3. All right, so it's in series with the inner and parallel with the two outer. Y'all follow me? Mm-hmm. And there's all these obvious permutations. Y'all with me on this class?
So that'd be one and then
series here, two parallel here.
Two parallel. So yeah, okay.
You got me? But that's problems that I typically give. Let me say that again. These are problems that I typically give things where you're going to, if you know what you're doing, you'll whip through it. If you don't, you'll fall on your face, usually. Always, because here's what people do. They're going to do something, they'll make an assumption. Okay, I'm going to assume current flow goes. What happens right here? Well, the same amount of current density isn't here and here. They're different resistance. All right, so what is constant? Well, the E field is constant between these two because the voltage will be the same between B and C. But it's a more difficult problem that way. I'm just trying to make it easy for you. Y'all with me?
Yeah.
Okay. So we could go through and do the same thing with cylinders. Did you have another problem for me to do? I'm trying to show you all the stuff.
350. Wasn't that just pretty much this problem just with the cylinder?
He's asking about it. What is it?
It's a similar problem. It's a resistance one, but it's with the cylinder.
Let's do a cylinder just for for completion. Do them all.
Okay. No, I think we should do 378 too.
This one's for finding the current. I think this is using a current density. I think.
All right. Go ahead and tell me the problem.
Okay. So we
Which
have
problem? Give me the number first.
350.
350. Got it.
Which one did you say? It's a columnar it's a column beam of
a column of
electrons.
Okay, so it's an electron density. Okay, got it.
From rho is 0 to rho is 1. From 0 to 1 millimeter.
Okay, so basically you got a column of electrons like that with a radius of A, and A is 1 meter?
1 millimeter.
Millimeter, is it going in the vertical direction?
It doesn't, we don't.
What does it say?
Plus AZ.
Yeah, it's in the AZ direction.
All right, go ahead.
Okay. And then the charge density is minus 0.1 cosine of pi rho over 2.
Okay.
Nanocoulomb per millimeter cubed.
Yeah, everything's in
Go ahead, what
millimeters.
did you run?
And a velocity of 6 times 10 to the 6 meters per second.
In AX or AZ direction?
Yes.
So the velocity is equal to 6 times 10 to the 6, right?
Yep, AZ. And
And
then
then AZ, and then that's meters per second. What does he want now? Correct?
And then rho, of course, is in millimeters. And then
Oh, this is millimeters per second?
no. I'm just saying rho is in millimeters.
Oh, okay.
All
right.
And then fine current.
All right. He wants the current. All right. Now, just listen. That's current density, right?
Yep.
In general, anytime you have,
That's charge density.
charge.
Is that the same?
Charge it. Anytime you have, it doesn't matter if it's a mass density, charge density, anything. When you want the total amount of charge flow, first, what is current in the simplest sense? I is equal to dq dt. It's a certain amount of charge that goes through some surface in a length of time. Y'all with me on this? Whatever surface. Here, he wants the amount of charge that goes through a surface of radius a right here per second, right? So we've got the velocity, right? Now, dq dt is in really coulombs per second, if you think about this, right? I want you to see this. So if we have this, and we want the amount of charge in that surface Q, the only thing we do is integrate this thing over the surface to get the total charge, right? And the surface would be from 0 to S. So I'm going to get total charge. You'll see this. We got velocity right here. Total charge is going to be equal to, it's a double integral because it's a surface integral of that charge density. I'll do it the way he does it. I don't like it, but I'll do it. 0.1 and it's times cosine of pi times rho over 2. And that's in the that's the surface charge density. This is nanocoulomb, so I'll put 10 to the minus 9th out front. Now I have to take the differential surface. The differential surface will be rho, and it would be rho d phi d rho. Are you all with me on this? You all with me? So in rho itself, if I went, d phi goes from 0 to 2 pi, and rho here goes from 0 to a. Y'all with me? And we're going to do millimeters. We're just leaving millimeters, okay?
Well, wouldn't the nano and the millimeters cubed cancel out? Because it's 10 to the minus ninth over 10 to
Well,
the 30th.
what I did is, I'm going to do the integration in millimeters. It's going to cancel, you're right. Here's what you're saying. If we go to meters squared, right?
If we went to coulomb per meter.
Then what's going to happen? If that's per millimeter squared, per meter squared, I got to multiply this by 10 to the plus third squared, 10 to the 9th. 10 to the 9th.
Yeah. Sorry, you said squared and
cubed.
Yeah.
Cubed. Are you with me?
Yeah.
Okay, anyway, before we can do this, let's, so if we want to do per meter squared, what's the radius 1 in millimeters? Let's do it this way. We're going to get rid of the 10 to the minus 9 because of that. Okay? Now, I'm going to get rid of the 10 to the minus 9. We'll do it in meters. We'll do it where the limit's going to be in millimeters, okay? So now the integration goes from 0 to 10 to the minus third meters. And now everything is an MKS system. Doesn't matter. You with me? All right, do the integration. Wait a second. Rho is measured in millimeters, right?
Yeah.
Well, then you got to take care of it here if you do that.
Okay.
Tell you what, we're going back. Let's do this. So this is going to be 2 pi, right? And then times 10 to the minus 9. And then I'm going to have minus 0.1. And then I'm going to have the integral of rho times cosine of pi rho over 2 d rho. And that's going to be from 0 to 10 to the minus third. Now, yeah, I think that's right. Okay, how do we do a x cosine ax integration? We could look at tables. We could break cosine up into what? E to the plus j pi rho over 2 plus e to the minus j pi rho over 2 times divided by 2, and then do an integration by parts if you want. You can look it up in a table, but that's a closed form integration. Is that how he does it with solutions, by the way?
No, in the solutions, he actually gets j first and integrates j over.
Yeah, but j is just velocity times the.
Yeah, he literally, all it is multiply that and then integrates that. So it's more or less the same thing you just did.
It is. J is simply going to be velocity times rho v. That's all it is.
Yeah.
And so he's just multiplying.
I think he does it that way because it cancels out the nanocoulombs and then other stuff first.
That's per meter second, right?
Yeah, but he makes it 6 times 10 to the 9th millimeters per second, and then he does it that way. And then he gets rid of the nano, and it's negative 0.6 cosine blah blah, and you just integrate that.
But he still has a rho cosine rho pi over 2 integration, right?
It's the same integration you're doing. It's just he uses different limits, and he has a different thing inside of it.
But do you follow me when I'm doing? We can do it.
It's the same thing basically. But
it's going to be, if you get j, you're going to take that, since that's meters per second. Like he said, it would be 6 times 10 to the 9th millimeters per second, right?
Yeah.
And since that's going to be times nanocoulombs per millimeter cubed, yeah, that's going to cancel. Anyway, it's going to be this form of integration, right? It's going to be Q times V at the end of the day. What's his answer? I'm curious.
His answer, like the total answer, it's minus 0.87 amps.
All right, minus point. Here's the deal. I'm not going to ask you that. I'm not going to ask you that kind of integration. So we can do. If you want me to do the whole formal thing, I will. But this integration is the key.
Yeah, that integration kind of sucks, but I mean.
Well, you could, that one, if you really want to do it, take cosine and turn it into cosine of theta is e to the j theta plus e to the minus j theta over 2. Then you have to do integration by parts.
Yeah, that would be a lot easier.
Or you can do just a table. Just look it up in the table, because I'm not going to ask.
Is that in the table?
I mean, I don't want to spend a lot of time with that. But you all with me on that, class? If you want to do the whole thing, we will. You got another problem or not?
I do. I'll see the table.
I do not like the millimeter business, but I understand.
Oh, there's one for cosine x too, actually.
All right, hold on for 1 second. Let me just erase this. I want to go through capacitance today.
This problem is about capacitance though, so that
It's capacitance. Let me go through the topic of capacitance. Now, I know you had it already in physics, right?
yeah.
So it's very similar to current density. So let me just give you a little brief intro to back capacitance, just like I did to resistance. When you talk about capacitance, really you're saying that if you have any 2 points where you got some Q1 here and some Q2 here, or a minus Q1, make it minus Q1. All right, you can assume these are conductors. There is going to be an electric field that is developed between this conductor and that conductor. It doesn't matter if this is a parallel plate, two cylinders, a spherical capacitor, you have an inner surface and an outer surface separated by dielectric. It really doesn't matter. Here's how you always do these problems. There's 2 ways. Generally speaking, you assume Q. You're going to assume Q. From that, you're going to get the D field. D is equal to Q over really the surface A. And a lot of times it's Q over 4 pi r squared if it's spherical. In cylindrical, it's going to be rho L over 2 pi rho per meter. And D field is always going to be the charge that you assume divided by the surface that the actual flux from that charge is penetrating. It could be spherical, it could be cylindrical, it could be planar. You all with me? Then after that, after you assume D, you get E. E is simply equal to D divided by epsilon. That's all it is. And epsilon is a dielectric between the 2 conductors that is usually epsilon relative to epsilon naught. I mean, that's the way it's normally rendered. You all with me? He'll talk in a book about something called a polarization, and polarization plus the D field is the E field. So something called the susceptibility is 1 minus epsilon relative, but don't worry about that. Just follow me right now with this one. We'll use epsilon relative. It's more common than anything. So once we have E, then we get the voltage, and the voltage is like before, E dot dl from part A to B, just magnitude. It's got to be positive. And finally, the capacitance times voltage is the charge on one plate. So that means the capacitance is just equal to the voltage right there, or I'm sorry, the charge, my bad. Charge divided by the voltage cos it. Now, I'm going to do these problems like I did the resistance problems. I'm going to show you the examples and show you the standard permutations. Y'all with me? And for this one, I'm going to do spherical first, then I'll do cylinder. All right, and we'll do your cylinder one. So let's calculate the capacitance of a standard 2-sphere problem, just like we did resistance, using that method. We'll do it for cylinders too, and we'll do it for parallel. But here, start off, I'm gonna say I've got an inner cylinder wall of not cylinder, spherical. This is a sphere. And an outer spherical surface of B. And it's filled with epsilon, just epsilon. Epsilon is epsilon. Epsilon here that I'm using is epsilon relative times epsilon naught. I'm not even going to worry about the value of epsilon. I still have a few minutes. Okay, you with me? Next, what I'm going to do, I'm going to find, so here I'm going to assume Q on the inner surface. So Q is here, plus Q. Outer surface is going to have an induced minus Q. From Q, I get D. Now, you know if I come out between the two, and I just draw a spherical surface at a radius r, I know that the integral of d dot ds over that radius is charge enclosed, right? What law is that, guys? Gauss's law. So I know the integral of d dot ds over the closed surface is the charge enclosed. I've got the charge enclosed. I know this is really 4 pi r squared times d of r is q, and therefore the d field is equal to q over 4 pi r squared 8r, right? Y'all follow me on this?
Yeah, that makes sense.
What's the E field? It's that divided by, it's D divided by epsilon, right? Now, here's a tip. Remember how I showed you I could change sigma versus position, radial position, in that resistor problem? I could make the epsilon value be a function of radial distance as well. Y'all follow me?
Yes.
So then when you divide this by epsilon, it may not be 1 over r squared. It could be 1 over r, it could be 1 over r cubed. You all with me? I could make it any function I want of radial distance as long as it was spherically symmetric, just a function of r. Follow me on this? So this is going to be, if it's constant, is q over 4 pi epsilon r squared. We're assuming epsilon's going to be a constant, 8r. Then, to get the electric field, and I'll do it over here, to get the voltage, probably. The voltage itself will be the integral from A to B. Technically, it's going to be, or from A to B minus that of E dot dl. I tell people, just get the magnitude because it's going to be positive. Can't be negative. So the voltage here will be equal to the integral, I say angle from A to B of the E field, which is going to be Q over 4 pi epsilon r squared AR dot AR dr. And I'll put a magnitude on that. The AR's cancel, and then I get Q over 4 pi epsilon. It's going to be 1 over B minus, 1 over A over 1 minus 1 over B. So that's the voltage. And finally, I get the capacitance by taking the charge divided by the voltage. Now, for this one, that means it becomes this. The Q's will cancel, and I get 4 pi epsilon over 1 over A minus 1 over B. Can y'all follow me on that? That would be the capacitance between the inner and outer surface. Do you remember what the resistance was for that same problem? If we assume, let's calculate resistance and capacitance. And this had a conductivity of sigma naught between the inner and outer conductor. What was the resistance? Do you remember?
Same thing.
Not same thing.
It'd be 1 over 4 pi sigma naught times 1 over A minus 1 over B.
Yeah, and let me show you a trick. Now, this is something you have to know. So anytime you have any two surfaces, and in between the surfaces, the epsilon and sigma value is a constant. This is important. It can't be a variable, it can't be a function of position. If it's a constant, then the resistance and capacitance between those surfaces, R times C, will just be equal to epsilon over sigma naught. Will always be that. If they're, and we're going to see it now. So what would the resistance be? I've got the capacitance. So this is saying the resistance, just based on this equation right here, the resistance would be equal to epsilon over C, right, divided by sigma naught. Take a look at this. All right, so it's epsilon over sigma naught. And what's 1 over C? Well, that's 1 over 4 pi, right, epsilon, times, and then it's going to be 1 over A minus 1 over B. Do y'all see this, class? You can see the epsilons cancel, and I get 1 over 4 pi sigma naught times 1 over A minus 1 over B, which is exactly what we actually did before, right? Yeah.
When again can we assume that the RC equals epsilon over sigma naught?
Anytime that between the two conducting surfaces, the epsilon is constant, doesn't vary positionally, not a function x, y, or z, or r, or anything like, and the sigma naught is a constant. That's a nice trick. You get one, you got the other from that.
So if epsilon or sigma, I guess,
Both have to be constant to use that formula.
I'm not talking about the formula. I'm talking about if they are a function of r, the only thing it'll affect is the voltage integration and nothing else.
The E field.
Yeah, it'll affect the E field, but
Or J. I'm sorry, or E, yeah.
which will in turn affect our
Affect
integration
V.
for the voltage.
That's right.
Okay.
That right. You're absolutely right.
Gotcha.
Just making sure.
That's cool.
You good on that? Can you see over there?
Yeah.
All right. Y'all with me? Now, that's a neat trick. So now, let's go to your capacitance problem.
It's 378. Let me read it out.
All right, hold on. Let me erase this, because I want to make sure, I'm trying to do this in a way where you can see the parallels. Very similar techniques.
That's a good one. Well, this is one where the epsilon changes. We can do one where the epsilon doesn't change if you want.
No, we can do that. It doesn't matter. We can do either one. Let's do the one where the epsilon changes.
Okay.
Go ahead.
Suppose a coaxial capacitor with inner radius 1 centimeter, outer radius 2 centimeters, and length of 1 meter is constructed with 2 different dielectrics.
Okay, hold. 2 different. Oh, this is going to be parallel capacitors, I think.
Yeah, I think so. And it says
All right.
when
Height H?
huh?
1 meter?
Yeah, that's how tall it is.
All right, half of it's made of epsilon 1, half of it epsilon 2 kind of deal?
Yeah, half of it's epsilon is 9, or epsilon r is 9, and half of it is equal to 4.
Okay, here's what I'm gonna start with, and you'll see what I'm doing. Let's just do the capacitance of something like this where this is epsilon, all right? Let's start there. So I got something 1 meter high, and it's a coax. So there's an interconducting radius, A, an outer conducting radius of B. Don't worry about the value. There's just the value epsilon here, whatever that is. Follow me? I don't care, but it's constant. So here's how we do this problem. And I think you're going to see and appreciate the way I'm doing it, I hope. So for this one, I assume charge, right? Now the charge I'm going to assume is the charge on the entire inner conductor. If you look at that, wouldn't that be like on a line charge? It would just be rho L. It would be rho L would be the charge Q over the meters, right? Let me just show you this. This can be looked at right here as just having all that charge on a wire. It doesn't have to be dispersed on just the surface. Do y'all with me in this class? So if I assume Q, rho L for that would just be Q over the height, which is 1 meter, or it would just be really Q, and this would be coulombs per meter, because it's 1 meter high, and that would be rho L. Now, I know if I have a line charge like this with rho L, you know, we don't have to do it this way, but you know, the integral of d dot ds, this is going to be something that's cylindrically symmetric. We're going to assume the D field is just radially outward. You all with me, class?
Yeah.
So for that, I think I remember this one. We have something like that. The D field is only going to be pointing in the radial direction, and therefore when I integrate d dot ds over the surface, what I end up getting is 2 pi times the radius, which is rho, and that's, this radius rho is between the inner and outer conductor. This is kind of drawn in a busy way, but what I'm really trying to show you is that if you're out a distance rho away, the D field is a function of rho, is what I'm showing you. So this is 2 pi. The D field, the integration of that is 2 pi rho times h times h, which is 1, times the D field, is equal to the charge enclosed. So therefore the D field is the charge enclosed over 2 pi rho h is 1, and that would be in the a rho direction coulombs per meter squared. I spent a lot of time on that. Did you all follow me? Total charge over the surface area. Now, there's a caveat here, and I gotta tell you this, it's assuming, and because this isn't actually true. Unless this is extremely long, then right at the top here, you would get some field fringing. You would have field lines with a D field that would actually have a component in the Z direction on top and the bottom. Do you all understand this? We're ignoring that. We're assuming primarily this thing is a very tall, there's very little distance between the inner and outer conductor. That's what we're assuming, like rolling up wax paper. I think I told you about that with capacitor making. Wax paper and aluminum foil to make a capacitor. That's the D field. What's the E field, guys? Just
That
D
over
field by
epsilon.
epsilon. Right? So that's going to be Q over, and this is going to be 2 pi epsilon, we're assuming it's constant, rho, and the A rho direction. Finally, what's the voltage?
It's the integral from A to B of E.
Okay, that's
Dotted with DL.
of E dot dl, right? And I'm just going to put it down. So that's the integral of this, which is the integral of 1 over rho, right, which is natural log. Do you all agree with this? No? I want to make light of it. But when I take this right here and I dot it, maybe I better show it. So when I go ahead and I take Q over 2 pi epsilon rho, it's A rho dotted with A rho B rho. And that's going to go from A to B. And that will be equal to Q over 2 pi epsilon naught natural log of B over A. And then finally, when I get that, right, that's the magnitude of the voltage. You all agree with that? How do I get the capacitance? Put it here.
Q equals C. So Q over B.
That's right. So capacitance is going to be what? Q over V, and Q divided by that, so it's Q over 2. That cancels. I get 2 pi epsilon naught over the natural log of B over A. And this is per meter, so this is going to be farads per meter. Do y'all follow me on this? This would be epsilon, actually, correct? He has that in the book, and you've had this in physics, I think, as a classic problem. Now, we're going to go ahead and talk about, well, what happens to the capacitance if instead of a full cylinder, it's half a cylinder? And I'm going to draw it over here. First, is everybody with me?
So that was for a full cylinder.
That's right. And that should make sense. Everybody follow me?
Yeah, it does.
Okay, I'm going to erase this. And I'm going to leave that up there. Your gut will tell you how to do this. So I'm going to look right down a z-axis, and I'm not even going to worry about trying to do a 3D perspective of this. But if I look right down the z-axis for this one, I see this. I see an inner radius of A and an outer radius of B here. Right? And I know the capacitance between here and here. Give me 1 second. So the capacitance between here and here is given by this. Are you with me, class? Mm-hmm. Now, what would the capacitance be if I had this, where I only had an inner radius of A, outer radius of B, epsilon, same height, but it's only half? What do you think this effective capacitance is going to be?
Pi epsilon over L and B over A.
Half of that. Do you agree with that?
Half of that, yeah.
It's exactly half of that. So it's like having the thing filled with epsilon 1 divided by 2. So this capacitance, and I've just called C1 here, will be equal to that capacitance divided by 2. It's going to be pi epsilon 1 and over the natural log of B over A, because that's half. It's dividing that capacitance over there by 2. C2 is going to be pi epsilon 2 divided by natural log of B over A. Does this make sense to everybody? I prefer to do it this way than any other way, because Most engineers got a good feel for parallel and series components. Now, do you all agree that that's really, now you got this problem, you got epsilon 1, epsilon 2. We can just say they're in parallel and add them up. Do you agree with that?
Yep.
So the total capacitance, see total for this one, that's going to be equal to the pi over natural log business I can take out front. And then I have to take epsilon 1 plus epsilon 2 here, and that'll be the total capacitance. Now, the pi stays as pi. What is the inner and outer radius?
4 centimeters and 1 centimeter. So
Right, 4. Natural log of 4, right? And then, and I'm going to put epsilon naught out here too. Epsilon naught, you can use that as 1 over, really, 36 pi times 10 to the minus 9 farads per meter is what we're supposed to have in some places. So this is what epsilon naught will be. What is epsilon for 1/2 of that dielectric? What is it?
For 1/2.
I mean, what does it give you for epsilon?
9 and 4.
9 and 4. It's
All
9
right,
for half and 4 for the other.
9 plus 4, that's 13. So it's going to be 13 times epsilon naught times pi over natural log of 4. Can you give me that answer?
I'm not sure what it is.
Y'all with me? This should equate to what he has.
Divided by natural. I got 2.61, or sorry, 0.261 nanofarads.
Anybody else?
I don't know if that's the answer.
Is that the answer?
I think he keeps it separated, but if you combine them in like parallel or however they're supposed to be combined, I think that's supposed to be right.
I guarantee it's right.
He's got these two. Shit. He keeps them separate. He keeps them like C1,
You gotta add
C2.
them up though, right? Does he ask for the capacitance between the inner and outer, or just the individual capacitance?
He just says calculate the capacitance, but he keeps it separate in his answers, which is kind of weird.
You gotta add them up.
Oh, he adds them up and he gets 522 picofarads actually.
What did we do wrong? Epsilon 1 is 9,
Yeah.
and epsilon 2 is 4.
Yeah, it's 4. I think the length is different. I think the natural one needs to be 2.
Outer radius is 2. I thought it was 4. My bad.
Outer radius
that
is
was the
different,
previous
too.
problem.
The outer radius is definitely 2 there.
Yeah,
So this
okay.
is going to be natural log of 2. So try that. See what happens.
Now I got 0.523.
That's what he has.
Yeah, that's right.
Okay.
0.523.
That's cool.
Nanometer. All right. You all with me on that?
Yeah, that's a lot different than what he did.
Okay. Another question. And then, y'all see if I change, if epsilon was varying, then right here, your E field would be different. Y'all follow me on that? Because the epsilon would be a function of rho, could be 1 over rho, could be 1 over, could be rho squared. Who knows? But that would be the difference. Y'all with me, class? You understand this? We'll do boundary conditions next time, and I didn't have time today. And you get a quiz. We'll do the quiz at the beginning. Well, wait a second. I take that back. If I get cleared, we won't do the quiz next. And I gotta, trust me, I gotta get permission. But if I get permission, I think I'm gonna. Then what I'll do is the quiz will be after the test. We'll go through the boundary conditions. I'll give you some more homework, and we'll do the sections in the book. Bear with me. I hope this is the way I'm going through this is okay with you. All right, good. So we have to do also boundary conditions, and then we do boundary value problems. But I'm just going to say this much. When you're doing anything like this, boundary conditions are going to be the tangent electric field across any surface will be equal, and I'll prove that. And then the normal component of the D field will be equal over any surface. That's the way it'll always be. After that, you're going to end up with this equation. Just bear with me so I give you a little peek at it. You remember you had E was equal to minus the gradient of the voltage. You all remember that? All right, now, what is divergence of D equal to? It was the volume charge density. What law is that, by the way? Gauss. Remember, the integral of D dot ds was charge enclosed. That's the integral form of it. That's the differential form. Do you all remember this class? And Gauss is my hero. I have several heroes. He's one of them. I mean, absolute hero. He's a brilliant, brilliant guy, and he always found a way to get rid of extra work. It's boring. So I love the guy. All right, so I have that. Now what's D? Well, D is epsilon E, isn't it? Right? So if you take a look at this, this becomes divergence of epsilon E equals rho V. If epsilon's a constant, divergence of E is rho V over epsilon. Do y'all follow me on that?
Yep. Yes.
Now, if I plug this right here, E is minus the gradient of the voltage into this equation, I get this equation. If I put divergence of E, which is minus the gradient of V, is equal to rho V over epsilon, I end up with this. I get del squared, it's a second order operator, on V is minus rho V over epsilon. And this is called Poisson's equation. Poisson's equation. I had a professor who used to call this Poisson's equation. Poisson's equation. And this we solve, it's a differential equation. We have, it could be in spherical, Cartesian, or cylindrical coordinates. And when we solve this thing for charge distributions, this is a differential equation. That's called a boundary value problem that we'll do next time. Yeah.
So next week is a review session for the test, correct?
Yeah.
And so I will. So
Wednesday.
Is capacitance the last thing that will be on the exam?
Yes.
So no Poissons.
Wow. Depends how many people show up for my Zoom. If I feel very neglected, then it's got to be no.
Okay.
So please show up.
I will. But capacitance was the end of the. I'm just making sure that's the end.
It's the end all be all.
Is that in the next chapter, Poissons?
No, it's in a section on boundary value problems. You'll see boundary conditions he does, then boundary values, then capacitance.
What chapter is this in?
Chapter 3.
I see it. It's right there. That's it.
And I'll go through this, but I want to tell you, I did this, I skipped over those two sections because the direct parallels between resistance and capacitance are overwhelming. That's the reason I skipped those. I'll go through that. Y'all with me?
Mm-hmm.
Yeah, most of this is a review from physics. There's nothing here that's astronomically earth-shattering in here. Thank you for recording.